Hey, welcome back to Falcon High School Chemistry. This is podcast 8.2, and our focus today is bringing it all together. Unit 6 was about converting amounts of substances from moles to mass to liters and so on, and Unit 7 was about balancing equations. So now we're going to use a balanced equation to convert amounts through stoichiometry. So let's get right to it. So the balanced equation for producing water is to add 2 molecules of hydrogen to 1 molecule of oxygen, which will give us 2 molecules of H2O. So we couldn't say that 2 grams of hydrogen combines with 1 gram of oxygen. That's not exactly what we mean here. So rather than saying that there's 2 grams of hydrogen, we mean there's 2 moles of hydrogen, and 2 moles of hydrogen weighs 4 grams. And that's going to combine with 1 mole of oxygen, which weighs 32 grams. And so we can't just take these numbers and call them grams. That's not what the law of conservation of mass means. Reactions describe quantities in moles. So your first step in a stoichiometric problem is to change grams to moles. When in doubt, go to moles. And then use the mole ratio. The mole ratio allows you to convert moles of one substance to moles of something else, moles of X to moles of Y. And then finally, you'll take your moles and go to the grams of what you're looking for. So this is the pattern that we're going to apply for solving all of these problems today. So here's our pattern. Let's apply it to example 1. So the same reaction, what's the path we would take to change 2 moles of water into grams of water? Well, that doesn't seem too bad, right? We'll start with moles, 2 moles of water. And we'll change it to grams of water. Since it's the same substance, I don't have to change moles of one thing to moles of another. I'm already here where I'm just changing moles to grams, right? So 1 mole of water, oops, that's got to go down on the bottom, so it will cancel. 1 mole of water is 18 grams of water. So we multiply 2 times 18 is 36 grams total. All right, well that wasn't too bad. That's just like a problem from Unit 6. Let's do something a little bit trickier. How many moles of oxygen are required for 36 grams of hydrogen? So now we're going to start with grams, go to moles, and then from moles of hydrogen to moles of oxygen. Moles of oxygen is our target here, so that's where we want to end up. You ready? We start with the number they give us, 36 grams of hydrogen, and we change this to moles. So grams has to cancel out. I want to make sure that crisscross cancels. And for H2, I need 2.02 grams per mole. Yeah? Can we call it 2 for the sake of simplicity? I'm down with that. All right, now we're going to change moles to moles and use your balanced equation. This is moles of hydrogen. Better write that in so that I make sure I put moles of hydrogen on the bottom. That way it will cancel out with what we had before. And then moles of oxygen is what I want to turn it into. So I put that on top. Now let's put the numbers in. Here's oxygen, here's hydrogen. So for oxygen it's 1, for hydrogen it's 2. The numbers come from the balanced equation. And now we're at moles of oxygen, so I'm done. Because look, moles of hydrogen cancel and grams of hydrogen cancel. So 36 is on top, and that's moles. And on the bottom, I have 2 times 2 is 4. Well, this is math we can do without a calculator, right? So I need 9 moles of oxygen to react with 36 grams of hydrogen. That's how we solve problems like this. Let's try another one. Grams of water produced from 6 grams of oxygen. All right, we're going to start with 6 grams of oxygen. So we're starting way over here. We're going to go all the way to the end. Follow the pattern. So 6 grams of oxygen represents how many moles of oxygen? When in doubt, go to moles. So grams has to be down here. 32 grams for oxygen because there's 2 atoms, right? So it's 16 plus 16. It's really important that you use complete labels in your T table because now in our next step, I have to change moles of one thing into moles of another, so I got to make sure that I have my moles in the right place. We're going to turn oxygen into water. So I put oxygen, moles of oxygen, on the bottom because in the previous step it was on the top, and I want it to cancel out. So in our balanced equation, oxygen is 1, and then water has 2 in front of it. So 2 moles of water comes from 1 mole of oxygen. And our final step is to change moles of water to grams of water. Make sure that you set it up so that crisscross cancels. So I'm going to put 1 mole of water on the bottom, 18 grams of water on the top. So now remember what we do. The top times the top times the top. So 6 times 2 is 12, and 12 times 18, I'm going to use a calculator for. 216 on the top. And along the bottom we have 32 times 1 times 1. I did not need a calculator for that step. But when I divide 216 by 32, I'm going to use a calculator for that one. I got 6.75 grams of water. Put a box around your answer because that's the way I like it. And so that's it. But I think it would be helpful for us to work through a couple more examples just so you can see other equations too. So example 2 takes us back to the same equation we used in podcast 8.1. I'm going to go ahead and skip these. Let's do something different. Here's the combustion equation. This equation describes the combustion of butane, which means combining butane with oxygen to create carbon dioxide and water and heat and light. This is the stuff that's in your candle lighter we use to light the Bunsen burners. So it says what mass of oxygen, that's our target, will react with 400 grams of butane. So we're going to start with 400 grams of butane in our T table, C4H10. And what's our first step always? You got it, go to moles. When in doubt, go to moles. That's what we do. So I put grams on the bottom and mole on the top. That way it will cancel. And this is moles of butane, C4H10. So let's add this up. Carbon is 12, so 4 carbons is 48. And then hydrogen is 1 apiece. So 48 plus 10 is 58 grams per mole. Now what's our next step? We changed it to moles. Now's the time where we use the mole ratio. This is the step where most students get stuck. We have moles of butane. We don't want butane. We want oxygen here. So I'm going to have to change butane into oxygen. We use the mole ratio then. So how many moles of butane? Our equation gives us 2 moles of butane for every 13 moles of oxygen. Great. Are we done yet? Not quite. It says mass. So we're going to change mass, change moles to mass. No big deal. We know how to do that. Use the molar mass of oxygen, 32 grams per mole, and we'll have it. Great. So every step along the way, I've put the numbers in my T table so that crisscross cancels out the units that I don't need and gets me to what I do want, grams of oxygen. So we're going to take the top times the top and then divide by the bottom. In your calculator, you might be tempted to just divide this number by 58 times 2. But if you don't use parentheses around 58 times 2, you're going to get this number divided by 58, and then the quotient would be multiplied by 2. Be careful, because that's not what you want. Oh, I didn't do 58 times 2 separately. I rarely do. 58 times 2 is 116. Okay, so my final answer is 1,434 point a whole bunch of stuff. I got all these calculator vomit. 400 is a number with only 1 sig fig, but let's pretend that there's a dot behind it so I can keep 3 sig figs. I don't want to round this to only 1. So let's see, 1434, let's just call that 1430. And it's grams of oxygen. Running off the screen here. Grams of O2. Put a box around your answer because that's the way I like it. You got it. All right, now let's talk about volume. Remember how to change volume to moles? What volume of carbon dioxide is formed? Well, we have to assume that this reaction is occurring at STP, and since it's a burning reaction, it probably isn't. So this is a great simplification, but that's all right. It shows us the steps to go through. So 400 grams of butane, C4H10, and of course we have to change that to moles. That's our first step. Wow, drawing crooked lines here. 58 grams per mole. I can't write the H10. My pen doesn't want to do that. It's the pen's fault, not mine. So now we have moles of butane. We want to get to carbon dioxide this time, right? So let's change moles of butane into moles of carbon dioxide. Look at your balanced equation and find that mole ratio. Here's our butane, 2. And then here's our carbon dioxide, 8. So make sure that you match them up with the right substances. And then moles of carbon dioxide will go on the bottom. For every 1 mole, how many liters will there be? At STP, it'll be 22.4 liters per mole. All right, I think we're there. So I have grams canceled, moles canceled, and moles of CO2 canceled, and I'm left with liters of CO2. Great, so let's do the math. Multiply across the top, 400 times 8 times 22.4, and then let's divide that by parentheses, 58 times 2, close parentheses. So I got 617.93, and I said in this step we wanted 3 sig figs. Hey, go back now. There we go. That's the problem we're on. So for 3 sig figs, I will get 618 liters of CO2. That would be important, right? If you're doing a reaction inside a closed container, you want to know that the container can hold on to all of the stuff that you produce. All right, well, that's example 3. Let's look at another one. All right, in this example, we have an acid-base reaction where hydrochloric acid is combined with aluminum hydroxide to form water and the salt known as aluminum chloride. So the question is, how many grams of aluminum hydroxide will react with 5.3 moles of hydrochloric acid? So I always circle the target so I know where I'm headed and underline my starting place because that's going to go on my starting line. So 5.3 moles of hydrochloric acid is my starting place. I'm already at moles, so my first step is to go to moles. I'm already there. So now I've got to change moles of one thing into moles of another. So I'm going to put moles of HCl on the bottom. Since I have it on the top in my step before, it's going to go on the bottom next. And moles of aluminum chloride is going to be on top of it because that's what I'm trying to change it into. Oh no, wait, wrong, aluminum hydroxide. Well, let's answer the question that they ask instead of the question I wanted them to ask me. All right, so look at your mole ratio. Here's hydrogen chloride, hydrochloric acid. Then here's aluminum hydroxide. Looks like we have a 3-to-1, 3 HCl's to 1 aluminum hydroxide. All right, so now I've got moles of aluminum hydroxide, and I want to get to grams. Well, you know what to do, the molar mass. For every 1 mole of aluminum hydroxide, how many grams are there? We're going to have to do some math here. Let's see, OH is 17, so I have 17 times 3, and I'm going to add that to aluminum. Good thing there's a periodic table right behind me. It says 27.0 for aluminum. So, what's that add up to? 78 grams of aluminum hydroxide for every mole. Let's take the top times the top and divide by the bottom. 5.3 times 1 times 78. And then we'll divide that by 3 times 1. Hey, I can do that math in my head all day long without a calculator. How about that? 137.8. That's too many sig figs. Let's stick with 2 since that's what we were given. We're restricted to 2 sig figs. So the 7 makes us round this up to 140 grams of aluminum hydroxide. There you go. So if you were going to weigh out the amount of aluminum hydroxide you needed to neutralize the hydrochloric acid, you would know to weigh out 140 grams. I think we've got one more. Yep, sure enough. So we have calcium chlorate decomposing, probably by heat decomposition, into calcium chloride plus oxygen. The question is, what mass of oxygen results from the decomposition of 1 kilogram of calcium chloride? Oh boy, they put in an extra step here, but that's all right. I remember how to change kilograms to grams, don't you? We're going to start with 1 kilogram. And how many grams are there in 1 kilogram? Let's put kilogram down below. There's 1,000 grams in a kilogram. That's what kilo means. So that's my first step, is get to grams so that I'm working on the same playing field here. And that's grams of calcium chlorate. So we're going to next have to use the molar mass for calcium chlorate. How many grams are in 1 mole of calcium chlorate? That's all right. Get your periodic table and get your calculator and let's add it up. Calcium is 40.01, and then chlorine is 35.45. How many chlorines do we have in this formula? This 2 multiplies everything inside the parentheses, so we better multiply this number by 2. And then oxygen, we have 16 grams per mole for each atom, and since there's 3 in a chlorate, we have 2 chlorates, that's 6 oxygens altogether. So add up this molar mass here real quick. I got exactly 207 grams per mole. Now what do we do next? We want to get to the mass of oxygen. Right now we have moles of calcium chloride. How do we get moles of calcium chloride to be related to moles of oxygen? This is where your balanced equation comes in. So I want moles of calcium chloride down here, calcium chlorate, pardon me, ClO3, and I want to change it into moles of oxygen. So now let's go up to your balanced equation and see what we've got. Right here, how many calcium chlorates? This number is just a 1. Since there's not a number there, that means there's only 1. And then 3 oxygens. Don't forget that mole ratio. Our final step, I'm running off my page here. I'm going to change colors so you can see. The final step is to change moles to grams. So 1 mole of oxygen is 32 grams because there's 2 atoms in every molecule, right? Okay, so now we've got kilograms canceled, grams canceled, moles of calcium chlorate canceled, and moles of oxygen is canceled out. We're left with grams of oxygen. That's what we were going for. Great, so take your calculator and multiply the top times the top and then divide by what's on the bottom. Use parentheses. Oh wait, we don't need parentheses because we just have one thing, right? It's 207 times 1 times 1 times 1. So just 207. All right. So out of 1 kilogram of calcium chlorate, we're going to get 463.768, blah, blah, blah. Bunch more digits. That many grams of oxygen. How many sig figs do I get to keep? We started with 3. So after the 3, that 7's going to make us round up. 464 grams of O2. Great. That's all there is to it. Once you get to moles, you're halfway there. So when in doubt, go to moles. That's my best advice. See you guys in class.